Good evening, folks. How's everybody doing?
Good evening, Professor. How are you?
Good, thank you. I hope we're all doing well. There's a lot of stuff going on right now, both inside and outside PCC. As you probably are aware, we're still on track to return to in-person instruction by next week, but everybody will have to go through a COVID test within 72 hours of going back to the classroom.
Actually, and then we already take it before the class start, and it doesn't count, right?
It has to be within 72
Oh.
hours. Yeah. So the school is offering a COVID test this weekend, Saturday, Sunday, and also Monday and Wednesday. So our class is a Tuesday class. So you have to get tested. If you want to get tested at the PCC, it's going to be Saturday, Sunday, or Monday, because they don't offer any test on Tuesdays. And I plan to go to get tested at PCC this weekend, because I don't want to, I don't want to be, rushing into the situation on Monday where everybody won't get tested. It's probably going to be a huge line waiting. So that's something to consider. And you have to have a negative test result in order to return to the classroom. Okay. Now I know this Omicron thing is different from before. A lot of people, especially young people like you, some people may be positive, but they don't feel anything, or they feel very little. But still, if you in the event that you got a positive test, please do not return to campus. Do not return to my classroom, but instead, you can send me an email informing me of the situation. What I can do is I can give you a virtual lab assignment so that you can do that at home. You're not going to lose any credit. Okay, assuming that you're still capable of doing it. If you're really sick, God forbid, if you're really sick, then of course, you just treat yourself as take care of yourself first. We can always worry about the assignments later. But if you are you have to be positive, but you don't feel you're incapable of doing things, don't come to the class, but I will give you a virtual lab assignment. Okay, so that's the situation, but things can change. I mean, they're still going to schedule a series of meetings over the next couple of days. It is possible that they may decide to postpone the return once again. So I'm sure you will be notified by that time. And if I hear anything, I will also post it on my class homepage, as well as making announcements on Canvas. So please, return to my Canvas class and keep yourself posted. Okay, so that is the situation. Hopefully everything will return to normal, and you guys all test negative, and me included. I have to get tested too. In the event that I get tested, I've never had a test so far. But if I get tested positive, and I'm feeling all right, let's say that's the case, then two things can happen. Okay, if one, I get a sub for you guys, or two, I do a Zoom lecture. Now, getting a sub is extremely difficult these days. So the school says that if I have a positive test and I cannot get a sub, then what I can do is to continue to do a Zoom lecture and give you a virtual lab. That way, you still have the credit for that lab, and so the instruction is not disrupted, except it will remain on Zoom for for a little bit longer. If that is the case, I'll let you guys know. Okay. Hopefully everybody will get tested negative and will come back and have an in-person instruction. So stay positive and test negative. Okay, that's our goal. All right.
So Professor, it means for every week, and we have to test this before 72 hours before the class, right?
Currently, that is the school policy. Yes, but as the pandemic eases, they may decide, oh, you guys don't have to be tested every week anymore. So, but as of now, that is what they're saying. Yes. Yeah. Okay, any more questions before we move on to today's lecture and lab?
Where is it going to be at PCC?
I think it's lot 3, parking lot number 3. Yeah.
Yes,
You guys
last
should-
time I take it from the lot 3 at the Hill Street Avenue.
Yeah, it's lot 3.
And then it's open all day?
What I saw over the weekend is from 9 to 3. And on Mondays, it will be longer because there's instruction going on. But on this coming weekend, it's going to be 9 o'clock in the morning to 3 o'clock in the afternoon.
Okay.
Yeah. If you go to the PCC website, even on the front page, I'm sure there's a link that points you that way. Yeah, so you get more detailed information about that.
And when we get the test,
Return next week.
and then
When do you get?
And then when we get the test, we just show you it when we get to class, basically.
Well, first of all, if you get a negative, if you get a
negative.
positive test, do not. You should leave the campus. Okay,
Yeah.
anybody, including me. And secondly, if you do get a negative test, yeah, then you can come to the classroom, but be prepared to show it to the instructor if requested.
Okay.
Okay, yeah, it's a rapid test that takes about 15 minutes for the result to show. Yeah. Okay.
Okay.
Very good. Any more questions? All right. So again, you will receive email notifications, and the school will also post information on the front page, and I will also post information on Canvas when it becomes available. Right. In the meantime, what we have today is we're going to talk about the first chapter of 1C, and also we'll be doing our first virtual lab. Okay, so the first chapter is chapter 15. I'm sorry, chapter 22/23. Reason why there are 2 numbers is because if you're on the 10th edition textbook, it's 22. If you're on the 9th or older editions, it's chapter 23. Okay. Either way, it's the first chapter in electrostatics. So let me share a screen with you. So with every discussion, I'm going to start with a summary of that chapter, whether this is a in-person discussion or virtual one, like what I'm doing right now. The assumption is that you guys have already studied this chapter, right? Am I right? I hope I'm all right. Okay, you have studied this chapter, you have seen the video lectures, you've done some homework and studied textbook, and here we're doing a review, a summary. Okay, and after that, I'll go over a couple of additional sample problems with you. We'll solve some problems together and answer any questions you have. And after that, we'll discuss the virtual lab associated with this chapter. Okay, so here's a summary of this chapter, electric fields. So what's the centerpiece of this chapter? Coulomb's law is one of the 4 Maxwell's equations. Okay, it's the first of the 4 Maxwell's equations, Coulomb's law. Coulomb's law deals with the electrostatic force between 2 point charges. Okay, so you know, it's quite clear what it says. You should be familiar with it by now. And what I really want you to do, as you saw in the video lecture, is to draw a comparison between Coulomb's law and the universal law of gravitation. These 2 forces are physically different. One deals with gravitation, the other deals with electricity, and yet somehow they share a lot of similarities. And that leads physicists to speculate that there might be some interconnection between these 2 forces. This connection, if you ask me, is there such a connection? You know, my gut feeling is yes, but where is exactly that connection? Is there a single unified theory to describe both static electric force, which is Coulomb force, and the universal gravitational force? Well, the answer is currently there exists no theory. This is still an unsolved mystery. Okay, but you really want to look at the similarities. They're both inverse squared. Okay, they're both inverse squared, which means as the distance between the 2 particles double, the force becomes 1/4. That's inverse squared over r squared. Why is it inverse squared? Nobody knows. It's just it's just an experimental fact. But what I can tell you, especially after you study the next chapter, it will become clear to you mathematically that the inverse squared law is unlike any other law That is, if the distance between two particles is r, and the force between them is 1 over r squared, that's called inverse square law, right? If it's not the inverse square law, if it's 1 over r to the power 2.1, or 1 over r to the power 1.9, or even 1.99, the situation is totally different. The inverse square law is mathematically unique. You don't see that from this chapter, but in the next chapter, you will see clearly why I say that. It has distinct mathematical features that makes it different from any other power. And this striking uniqueness, plus the fact that electrostatic force and universal gravitational force both satisfy the exact same law, really tells us there's something to it, you know, there's just something behind it, something more fundamental, but we're still in search for that. We don't know. All right. But you will see clearly why the inverse square law is such a unique law in the next chapter, when we rewrite Coulomb's law in a different mathematical form called Gauss's law. You will see that. Okay, so so that's a striking similarity, but there are, of course, differences. The most important striking difference between Coulomb's law and universal gravitation is, you know, gravity is always attractive. Okay, here in the case of electric force, there are two types of forces, attractive and repulsive force. And this is the reason why we need two types of charges, positive and negative. We call them type positive, the other type negative. And if you put like charges together, positive or negative, they repel. You put dislike charges, positive and negative, they attract. This is true for electricity. It is not true for the law of gravitation. And that really works out because gravity is generally a very weak force. Okay? The force between you and me, gravitationally, the force is not zero, but it's very, very small. The force between two skyscrapers, gravitationally, it's also very small. Okay, so even though there's always an attractive force between any two objects in the universe, that force is usually very, very small, unless one of these two forces, one of these two masses is of astronomical magnitude, such as the force between the Earth and the Sun, and so on. So gravity is important when it comes to large structures. You know, what causes the Earth to go around the Sun, what causes the Sun to go around the center of the Milky Way, how galaxies come together, that sort of thing. So when it comes to large scale phenomena, because of the astronomical masses, gravity becomes the dominant force. Okay, that's the role of gravity. But what glues the molecules of a table together? That is not gravity. Okay, any solid that you see, the reason why they're solid is because the molecules are just stuck together, right? There's an attractive force between them, they don't break apart. That force is not gravity because gravity is too weak. Okay, the mass is pretty small, you know. What force does that? That's the Coulomb force or electrostatic force. So gravity holds different parts of the universe together, and the Coulomb force holds everything else together. Okay, and so that's an important distinction, and it's a good thing that it comes both attractive and repulsive. It's not just attractive or not just repulsive. Reason why that's important is because the Coulomb force is extremely strong compared with gravity. And if it's only attractive, everything will just crash together. If it's only repulsive, everything will just fly apart. You have to achieve a balance, and that balance is achieved when the positive and when the attractive force and repulsive force they sort of cancel each other out. That's how we reach a balance. Okay, so that's an important difference. And when we study the Coulomb's law, we notice, for example, the direction of the force between 2 point particles is along the line connecting them, right? Along the line connecting them, and that is an experimental fact, but it can be deduced theoretically. It is not something surprising. It is from so-called symmetry considerations. And I have given you an argument in my video lecture why that's the case. Symmetry is of extreme importance to many physics problems, and you may not have seen a whole lot of that in physics 1A, 1B, but you're going to see a lot of that, a lot of symmetry arguments that I'll be making in physics 1C. It will greatly simplify your calculation sometimes. Okay, so that's the general overview of Coulomb's law and how compares to universal law of gravitation. But the next task is that once we know Coulomb's law, how do we calculate the electrostatic force between charges? Now, of course, it's a point charge, 2-point charges, that's Coulomb's law directly, right? We already know how to do that. How do you calculate electric force between a chunk of positive charge and a chunk of negative charge? Well, these are not point particles. They're not point charges. So we need to extend Coulomb's law to include extended charges, say a charged sphere, a ring, that sort of thing. That is a jump. That is not included in Coulomb's law. Coulomb's law only talks about point charges. How do you go from point charge to finite size objects? That takes some additional law, what's known as a principle. What is that? The superposition principle. Okay, oftentimes people take that for granted. They say, oh, that it goes without saying. No. Cannot say it goes without saying. The superposition principle has never been proven theoretically. I can tell you that. Nobody knows why, but we do know that it works. How do we know it works? Because it agrees with experiment. Okay, so we say it's a principle, not a theorem, not something we derive. It is independent of Coulomb's law. It's just something we found to be true experimentally. And what does it say? It says that when you consider the force of a whole bunch of charges, not just a point charge, what you can do is divide this chunk of charge into really, really thin, extremely small particles. Each particle is a point charge. And you find the Coulomb force between this point charge and that point charge. And all you have to do is to add all these little forces together, point charge between point charge and point charge, between another point, just add them all together. It sounds obvious, but it's actually not. There's no part of Coulomb's law that says that if you look at anything beyond a point charge, you still retain Coulomb's law. Nobody says that. It's just found from experiment. But we know it to be true from countless experiments, so we're going to use it. Okay, so what that means is that if I want to calculate the electric force between, say, 3 charges and 1 charge there, what I have to do is to find, I labeled these 3 charges, 1, 2, 3, I labeled that one number 4. What I can do is find force between 1 and 4, force between 2 and 4, force between 3 and 4, and add all these 3 forces together. Each force satisfies Coulomb's law. Okay, that's what I would do, just summation. Examples of particular interest includes dipoles and multipoles. Now, I did mention that, I did talk about that in the video lecture. But perhaps more importantly is a case of continuous charge distribution. That is, you don't have just point charges. You have, say, our charged sphere, our charged disk, our charged cube, that sort of thing. A charge distributed on an extended object. What do? You don't have point charges. Well, that's when calculus comes in, folks. Okay, how does calculus work? Why do we need calculus? Well, oftentimes we only know how to deal with an infinitesimally small object. If the thing is infinitesimally small, so the volume is infinitesimally small, or the area is infinitesimally small, the length, we know how to deal with that. When you have an extended object, we don't know how to do that directly. So the idea of calculus is that since we don't know how to deal with everything, in one continuous setting, we'll cut it into pieces. Okay, take a charged sphere, for example. We chop it into infinitesimally small pieces. Each piece is a point charge. Why do we do that? Because we know how to deal with a point charge. It's Coulomb's law. Coulomb's law deals with point charges. Okay, so we divide it into infinitesimally small pieces. Each piece has a charge dq. How much force does this dq produce on somebody else? We call this force df. Okay, that process of chopping pieces is called differentiation. Then you get df from Coulomb's law. What do you do next? You have to add all these df's up, right? The principle behind that is what? The superposition principle. You are able to do that because of superposition principle. And then you have to add all the little df's up. That process is called what? Integration. Okay, so that's what calculus comes in naturally. Okay, now in 1A, when I teach 1A, I try to avoid calculus as much as I can. Most of the problems you see in 1A are not calculus based. Most of the problems. In 1B, we start to use more calculus. In 1C, It's just mostly calculus. That's the language we use. So, but I'm sure you guys are more well versed with calculus by now. You are veterans now when it comes to doing calculus, right? Three-dimensional calculus. Okay, so that is the plan. We take this object, right? Cut it in pieces. Each little piece produces a force dF. We add all these dFs up by integration. That's what we do. How do we do that for each problem? It depends on the geometry of the problem. Okay, and we don't do the most general examples because the integration becomes impossible to do, or very hard to do. We look at some examples, special cases. What are the cases that we see the most often that you have to know how to do? A rod, for example. Okay, you have a uniformly charged rod. Right? What is the electric force? Somewhere along the line, away from the rod, or somewhere above the rod, somewhere below the rod. You have to know how to do that. What about a loop, a circular loop of uniform charge? Now, for that problem, I only want you to do the electric field, the electric force from that loop on a point charge located on the axis of symmetry of the loop. Okay, you have this loop and you have another point charge on the axis of the loop. You should know how to calculate that. That's a classic problem. It's in my video lecture. It's also in the textbook. Do not worry about how to calculate the force between a loop and a point away from that line of symmetry. That problem becomes mathematically a whole lot harder, and it's not something you would know how to do in physics 1C. Okay, you know the principle, but you don't know how to do the integral. All right, what about a disk? A uniformly charged circular disk. How do you find the electric force between this disk and, say, another point mass on its axis, point charge on its axis? Well, if you know how to do a loop, you can think of the disk as made of a whole bunch of concentric loops, right? Each loop has a little charge dq, and you know how to find the electric force from that little loop. You add all these loops up, you get a total force. So here you see some one-dimensional, two-dimensional examples. One-dimensional, a rod; two-dimensional, a loop or a disk. What about three-dimensional objects? These seem to be very common, right? A uniformly charged sphere, a uniform charged cylinder. How do you calculate the electric force, say, between a uniformly charged sphere and a point charge outside? That is not something you want to do in this chapter, at least not easily. Okay, if you're very well versed with calculus, you may know how to do that. Okay, you may know how to do that. But turns out that for problems like these, especially for uniformly charged sphere, there is a special technique which allows us to find the solution to this problem with far greater ease. And that's something you will see in the next chapter. And that next chapter, like I said earlier, is based on the special nature of the Coulomb force being 1 over r squared. Only when it's 1 over r squared will that method work. And that method is called Gauss's law, which is a mathematical variation of Coulomb's law. You will see that in the next chapter. How do you calculate the electric force between a uniformly charged sphere and a point charge? You want to do it with straight calculus, it's going to take you, a lot of time. You're gonna have to cut this, cut this sphere into pieces, right? And you can choose to cut it into parallel slices. Each is a little disk, but of different size, right? Different radius, right? And different distance to that point. It's a mess. But if you use the method that you see in the next chapter, you can do this entire thing using a more elegant way, and you can complete the answer, obtain the answer in 10 seconds. Or maybe 20 seconds. So, it's going to be a whole lot easier. So we will delay that until next chapter. Okay, but those examples that I mentioned here, rod, loop, disk, you should know how to do that. Okay, and now we have been only talking about electric force and electric charge. What about electric field? Okay, after all, that's the title of this chapter, electric field. Well, the concept of the electric field is such that when, let's say I'm in this room, right? Somebody next door had a charge. I cannot see it. I cannot see it. How do I know somebody had a charge next door? Well, what I can do is if I have a test charge in my hand, a little positive charge, I hold this charge in my hand and say, gee, this charge, somebody is giving it a force. I can see the charge, it's trying to fly away from my hand. Somebody's giving it a charge. a force. How much is the force? I can measure that, right? I can measure that. What if I double the amount of charge that I hold in my hand, double that test charge? I'm going to receive double the force, obviously, right? Double the force from a source, unknown source next door. And what if I triple the amount of charge I have in my hand? I'm going to triple that force. So the force that this test charge experiences depends on how much test charge you have. It's proportional to it. But what if I take that force, right, that I get, divided by the test charge? I take the F divided by Q. Will that ratio still depend on the test charge? No, because when I double the test charge, I also double the force. The ratio stays the same. That ratio no longer depends on the test charge, but it does depend on how strong that source is next door. If the source is strong, I'm going to get a greater force. That ratio is called what? The electric field. Okay, so an electric field can be tested with that test charge. And it's independent of the test charge. It only depends on where the source is and where that location is. That's the electric field. Now, the definition of the electric field goes beyond that. Okay, what if I don't have a test charge in my hand? So I cannot test it. I do not know how much the electric field there is because I cannot test it. I cannot do this experiment. Does that mean the electric field does not exist in this room? Well, the answer is no. The electric field still exists, whether or not you choose to test it. Okay, just like there's somebody next door. It doesn't matter whether I know there's somebody next door. That person exists next door. Okay, in a case of the electric field, if I have a test charge, I can measure it. I can figure out how strong the field is. But even if I don't have a test charge, the field is already there because, as you will learn in a later chapter when we talk about energy associated with the electric field, when somebody brought a charge next door, that person just established an electric field that permeates through this room, assuming the field goes through the wall, okay? The field is real. It doesn't depend on any test charge. It is already there. Why? Because the field brings extra energy to this room. Anything with energy is real because energy and mass are related with Einstein's famous equation of E equals mc squared. When somebody put a charge next door, that person, believe it or not, has increased the mass of this room. Of course, that's real, right? Anything with mass is real. But of course, it's just a tiny, tiny, tiny bit. Okay, you're not going to be able to measure that. It's too tiny, but it's there. Okay, so electric fields are real. They do not depend on the test charge for its existence. The test charge is only there to measure how much it is. Okay, you will see the concrete evidence of the electric field carrying energy later. Okay, so those are the summaries for this chapter. For this chapter, so we have the Coulomb's law, the conceptual version part of the Coulomb's law, along with the electric field concept. We also talked about how to calculate the calculation, calculate electric field, electric force of these special cases. Okay. Now, one thing you have to realize in physics 1C is that most of the time the calculation will get so hard that you don't know how to do it. We're looking at only a very special, small set of cases where the calculation is simple enough that we can do it, such as the force between a uniformly charged circular ring and the point charge on its line of axis. Yeah, we should know how to calculate that. Once that point leaves that axis of symmetry, the calculation becomes more than 10 times as hard. It's not something you physics 1C folks can handle. You will have to go to graduate school to know how to do this. And even in graduate school, the calculation is it's very messy. Okay, so you see a lot of cases where the mass really just drowns you, in it comes to electricity and magnetism. But don't worry about that for now, because in 1C, we only select a small amount of problems whose math is simple enough. Okay, it doesn't mean 1C is too simple or useless, because the concepts we learn in 1C is there. It's just that mathematically, we are limiting ourselves to simple cases. Okay. So that is our overview of chapter 22/23. Do you have any questions? All right. So what I want to do now is I want to take you to a couple of sample problems that we want to work together. So I am going to share another screen with you. I'm going to work things out with you together. Okay. I've already posted these two problems as a preview. Okay. So you may have already seen it, and that's what I hope you have seen it. And some people may have already attempted it, but other than that, we're going to work things out together. Okay, so let me do a new share with you. Okay, you can see the picture, right?
Yes, Professor.
Okay, very good. So let me show you how that works. So here we have two additional sample problems. This is one of them. So here you have some sort of review problem, because it brings us back to physics 1B, simple harmonic oscillation. So what you have here is everything happens on the x-axis. Okay, so you have a pair of fixed positive charges, positive q and positive q. They cannot move. Okay, and the distance between them is 2a, too small a. So this guy here, let me this distance here is a, and this here is also a. Here is the center, the original coordinate system at x equal to 0, the midway between the two positive charges that are held fixed. Now I have another positive charge, small q. Okay, and if small q is located right in the middle at x equal to 0, of course the force it receives from both sides will cancel out, right? The net force is 0. When the net force is equal to 0, it is in mechanical equilibrium. So we call it equilibrium position. Remember that from physics 1B. Now suppose I push the small charge to a distance positive x, by a distance positive x. Okay, this is positive x. Then it's going to lose balance, right? It receives more force from the charge on the right because it's closer, and receives less force from the charge on the left because it's further away. So the net force now points along the negative x direction. And that tends to push it back to the equilibrium position of x equal to 0. Right? Similarly, if you take that charge of positive q, you move it along the negative x-axis, then it's going to get more pushing force from the charge on the left and less one from the right, and then the net force is going to point along the positive x direction. So either way, as you take that positive charge q, small q, away from equilibrium, you're going to get a net force pushing you back to x equal to 0. So as a result, it's going to enter an oscillation. Okay? And we want to show that if x is small compared with a, then I want, okay, absolute value of x is much less than a. I want you to show that the resulting motion of this small charge small q is simple harmonic. And I want you also find the period of the oscillation. Okay, you recall the condition for simple harmonic oscillation. The force acting on it cannot be just any force, must be what's called a linear restoring force, and that is F must be equal to a negative constant k times x. Okay, this k could be a spring constant, could be something effective, similar to a spring constant. Okay, so if we can show the force looks like this, negative constant times x, then you know it's a simple harmonic oscillation. So let's find the force, shall we? Let's find the force. The force comes from both charges. So using the positive x direction as pointing to the right, then the force from the left charge is positive. The force from the right charge is negative. Okay, so force, the net force, equals to. First, let's take the positive force, which is the force from the charge on the left, and that is k big Q small q over what? The distance between them, which is a plus x squared, right? A plus x. And then the force that's negative, which is the force from the right, pushing it to along the negative x direction. So it's minus KQQ. The distance between the red charge and the charge on the right is a minus x. So a minus x squared. Right? Clearly, the first term is less in magnitude than the second term because it's got a bigger denominator. This force is nothing like constant times x. You know, it doesn't remotely look like this because x is in the denominator with a square. However, as we make an approximation of using x is far less than a, we're going to see some interesting transformation, simplification. So let's do that. Okay, let's do that. So what I'm going to do is I'm going to take that. I'm going to take that a out. I'm going to go KQQ over a squared. Okay, I'm going to take that a out. And the first term is 1 plus x over a squared. Okay? I didn't do any approximation. It's just the same as before. I can do a similar, I can do something similar for the second term and take the a squared out. There's a common factor in front. This is the common factor in front of it. Okay. And then minus this. I'm sorry. It is 1 minus x over a. 1 minus. So there's no approximation here. Okay. But next, I'm going to do an approximation. I know that x is far less than a in magnitude. So x over a is a lot less than 1. Okay? Now, when you take 1 plus alpha to the power n, when alpha is a number that's very close to 0, when absolute value of alpha is far less than 1, what is this approximately equal to? Well, if alpha equals 0, then you just get 1, right? But if alpha is not equal to 0, what's the first term that pops up here? Anybody? That, in fact, is the first term in Newton's binomial theorem. You can also use Taylor expansion to find what that next term is. The next term is n times alpha. Okay, this is from your math class. And it's one of the simpler cases, but extremely useful. Are you familiar with that? If not, please review that. So with that approximation, so in our case, alpha equals to x over a. Now we know absolute value of alpha is far less than 1. So therefore, with that in mind, I'm going to approximate f now. So f roughly equal to what? Keep these constants, KQQ over a squared. And look at the first term here. Look at this term here. Okay, alpha is x over a. What's n equal to in this term? N equals what? -2, right? Why -2? Because it's in the denominator. Okay, so this first term is roughly what? 1 plus n alpha. N equals -2. So 1 minus 2. Alpha is x over a. That's the approximation. So now you see, I have flipped x to the numerator, and it's the linear, which is good, which is what I'm looking for. I want the force to be linear to x. Okay, now let's look at the second term, minus what? The next term is just like the first term, except there is a negative sign instead of positive sign. So the next term is 1 plus 2x over a, right? Because n is, once again, -2, but alpha is negative x over a. So the two negative signs cancel, you get a positive sign. Okay, you see clearly we can cross out 1 and 1 here. And what's left is -2x over a and minus 2x over a. You can combine them. That becomes -4 KQQ over a to the power 3 times x. See that? And now we realize that this force is a negative k times x, where k equals this constant here, 4 KEQQ over a to the power 3. Okay, anytime the force, net force exerted on this object is equal to negative constant times the displacement away from equilibrium, you get yourself a simple harmonic oscillation. Recall from physics 1b that so standard simple harmonic oscillation for mass and spring system, I have mass times acceleration equals to negative kx. Remember that? Okay, and the solution to that problem, if you recall from physics 1b, is simple harmonic with the period t equal to 2 pi times the square root of m over k. Okay, that's the standard solution for simple harmonic oscillation. In our case, what is the solution to, what is the equation of motion for our case, for the red mass in the middle, red charge in the middle? Ma equals what? Negative k. Why don't we just call it effective k effective. Negative k effective x. Our case, this charge also satisfies this equation. So therefore, it's got to be simple harmonic, and the period is 2 pi m over k effective. K effective is 4k EQQ over a to the power 3. M over 4k q over a to the power 3. There we go. So this is the simple harmonic oscillation, and here is the period of that motion. Okay, so this is a combination of Coulomb's law and simple harmonic oscillation. Questions, folks? You guys can hear me, right?
Yes, Professor.
Okay, good, thank you. Yeah, I sometimes I'm a little spooked when I hear there's no sound coming from you guys. Okay, so let me know if you have any questions or need me to clarify anything. Okay, if you don't have anything immediate, let's look at the next problem. The next problem is more, it's just about E and M. There's no physics 1b or 1a stuff in it. And this one requires some integration. It says a positive point charge Q is located at distance A above a very large plane of positive surface charge density sigma. Sigma is charge per unit surface area. Okay, so you have a very, very large, you can think of an infinite large sheet of charge. Okay, you want to find the electrostatic force exerted by the point charge from the plane. So how much force does the plane give to that point charge? Now we know the direction of the force is up. It's vertically up. Can you see why? Anybody? How do we know it's for sure it's going to be upwards like this?
Because
what's wrong? I'm sorry?
But the sheet is positively charged and the Q is a test charge. This is positive. That's why the same charge repel.
Yes, they repel. I agree. How come the force cannot be like this? What's wrong with that?
Because it's not moving.
I'm sorry?
Because the charge is not moving actually. So that's why the force has got to be directly positive direction of the gravitational force.
There's no gravity here in this problem.
I mean, like the repel.
Okay. This is an example of how symmetry arguments can lead us to simplified answers. Okay, what is symmetry? Say you have symmetry between, you have symmetry on your face. Okay, a normal human face has symmetry about the middle vertical line passing through the middle of the nose. So that means if you look at the left side or right side of the face look the same. That's an example of symmetry. Symmetry means you take an object, right? And you do something to it, let's say you rotate it, you flip it over, whatever. And as a result, it doesn't look different. That is called symmetry. Okay, you do something to a system and the system looks unchanged. That is called symmetry. Now, in our case, okay, you have a very, very large uniformly charged sheet. Imagine you have this axis here, okay? This axis that passes through, that's passed through the point charge Q, and it's perpendicular to the sheet. So you have this axis like this, okay? Axis like this. What's going to happen if I were to rotate the sheet about this axis, like this. Imagine spinning that sheet. Tell me, does that change the force? Should it change the force?
No.
No, because sigma is the same everywhere. You wouldn't even know the thing's being rotated. That means the force F cannot change, can it? Because nothing happened, everything looks the same, right? The force shouldn't change, right? Agree?
Yes.
On the other hand, if the force points this way, what do you think happens when I rotate the sheet? If the force points this way initially? Well, I mean, the force has to rotate together, right? Because the force depends on, on the sheet. If the sheet turns by 180 degrees, then the force also turns 180 degrees. The force goes over like this, right? Agree?
Yes.
But that's wrong, because the force shouldn't change. Right? The force shouldn't change, because as I turn about this axis, you retain symmetry, nothing happens to the force. You know what that tells me? It tells me the angle theta here can only be 0 degrees. Okay, which means the force has to point directly away, because only when theta equals 0 degrees, then as we turn the sheet about this axis, nothing happens to force. So that's the only possible way. See that? So that is a symmetry argument telling us the direction of the resultant force. Okay, so I'm going to erase these now. I know the force is pointing directly away, has to point directly away. Okay, has to be like this. The force has to be like this. Okay, that's my first argument. Now, how much is that force equal to? That's what I want to know. Okay. Well, there is a simple way to do that in the next chapter, but before we get to that, I want you to use our conventional Coulomb's law to see how we can solve this problem. Now, because we have a infinitely large sheet, I'm going to have to cut it into small pieces. If you don't know, if you have nowhere to start, you can cut it into, infinitesimal small parts, but that's a lot of cutting to do. I can make things a little bit easier by cutting into the two typical ways of doing that. I can cut it into a whole bunch of concentric rings. Each ring, I know how to do that because I found the result. Okay, that's one way, but I'm not doing it this way. I'm going to do another way of cutting. I am going to cut it into a whole bunch of parallel strips. Infinite long parallel strips. Because I know how to find electrons from each strip already. This is a sample problem that's being worked out. Recall the solution to this problem. If you have a very long linear, very long line of charge with linear charge density lambda, the charge per unit length, and I have a point charge here with a distance of r. What charge, if this charge is q, then what kind of force does this linear charge lambda give to that charge q? This is a problem that's been already worked out as a sample problem in this chapter, and I know the force is k q lambda over 2 pi r. Okay. That problem, that problem is being worked out. Now, given this as our starting point, what I'm going to do is I'm going to cut this into parallel slices. So here's a parallel slice. It's just like one of those very long rods. I know the electric force from coming from this long slice to at that point charge. Okay, to make it easier to draw, I'm going to look at it this way. I'm going to change my perspective. I'm going to look at it this way. Okay, so imagine that you are looking parallel to the sheet, looking this way, and then I can redraw this picture. So the picture looks like this. I have this slice. This is the cross section. It's just right here. It's just like right here. Okay, then I have this point charge. I have this point charge here. This point charge here. Okay. The distance is still a. This distance is still a. So here is, here's a side view of the sheet, And I'm looking at a little slice here, this little slice here, which is this slice here. Okay, the distance between them, I call it R. Okay, I call it R. And so for this little sheet here, for this little slice here, which is this little slice, is receive the force, the charge Q receives the force this way, which I call dF. dF. Okay, what is the magnitude of dF? Right here, that's the magnitude of dF. Okay, if I can find what lambda is, right? Now, the final force is not pointing this way, it points along this direction. If this angle is theta here, all I care about is the component of dF along this direction, because only this direction eventually survives. Okay, so what I need to do is to find dF times cosine theta. That's what I really care about. Okay, this is the force from this little slice, from this little slice, which is the same as here. Okay, then what I need to do is to add all these slices up. I have to do this, right? I have to do this. That gives me the total force, right? Total force. I'm adding all these slices up. Am I making sense so far? Okay, this R here, I can draw this R here as well. This R here, that's the R I'm talking about, this R here. Okay, it's the same as this R. See this picture. Okay, this is the angle theta. Right? So my job is to find dF cosine theta and integrate it. So what's dF now? dF is kq lambda over 2 pi r. But what is lambda? Lambda is the charge per unit length along this little slice, Now this little slice had a certain width, okay? At a certain width. If I call this the x-axis, so the x-axis goes this way, okay? If I call this, here's the origin is right here, okay? This distance, I call it x. So the thickness of this slice here is dx, okay? The thickness of this slice is dx. So let me look at this little slice more carefully. So you have this little slice with the thickness of dx here, infinitely long. What is lambda for this slice? I want to know. Lambda is charge per unit length. Okay, so charge per unit length, lambda. What is the charge per unit length? Look at this slice here. If the charge density per unit area is sigma, right? So then charge per unit length would be sigma times this area of thickness dx and the length of 1 unit, right? 1 unit, because that's unit length. Lambda times dx times 1, okay? Isn't that lambda for this little slice? Okay. So we know lambda now. So therefore F equals to dF, which is k q lambda. Lambda is q sigma dx divided by 2 pi r. Okay, and then there's a cosine theta. Hey, are we still together so far? Now we have to, before we can integrate, we have to clean things up a little bit. There are too many variables here. There is, because there is a x that varies, there's a theta that varies, there's an r that varies. There are 3 variables. I don't like that. I want to change everything to a single variable. Okay, you can kill x and r and keep theta, for example, or you can kill r and theta and keep x and so on, because you can only integrate over 1 variable. Okay, now R is, look at R here, look at this right angle triangle here. This right angle triangle here. This right angle triangle here. R is the square root of a squared plus x squared. But cosine theta is a over r. So I can simplify things a little bit here. I have cosine theta equals a over r, right? So I have this f as, I'm going to take these constants out now. K, Q, sigma, and 2 pi, all these are constants. And cosine theta is a over r, there's another a out. And then you have dx, and you have over r squared, right? right? I'm just plug that into here, okay? So I no longer have theta anymore. I just have x and r. Okay, but still there are two unknowns, two variables, x and r, and I need to get rid of one of them. So for example, let's get rid of r. How is r related to x? Again, you going back to this right angle triangle here, you have x, you know, a is a constant, okay? A is a constant, so you have x equals to, okay, you want to express, okay, you know what? I can get rid of r in favor of x, but the problem with that is that those of you who did calculus, this becomes a math problem. Okay, I've established the physics already. This becomes a math problem. When you do something like that, I don't know if you have this this feel. When you do something like this, this r is the square root of x squared plus r plus a squared. When you work out integrals like that, you frequently have to use trigonometry substitution, don't you? Right? You define an angle theta and so on. So, I mean, you can get rid of theta for now, but eventually when you work out this integral, theta is going to come back. That's how you work out this integral, you know, using trigonometry substitution. So why don't we do this? At this point, I'm going to write x in terms of theta and also r in terms of theta. So theta becomes my final variable. I'm going to integrate over that. Okay. If you have a better way of integration to finish this integral, you don't have to listen to me. But let's work it out together. Okay. You know, sometimes, especially in the past, I've told my students, once we went this far, it's your job to finish the integral. But then I realized that some people may not be all that familiar with, all that comfortable with integration, which this course relies heavily on. So let's work it out together. Okay. So I want to replace x and r both with theta as a variable. Remember, a is a constant. Okay, so how do you replace x with theta while keeping a there but not r? R, because r is another variable. Clearly, x over a equals tangent theta. So that's what I'm going to start from. Okay, I go x over a equals tangent theta. So therefore, x equals a tangent theta. But I have a dx there, so I'm going to differentiate. So let's do that, okay? So dx equals what? What's the differential of tangent theta, folks?
Is that a secant squared?
Yes, secant squared. D theta, there we go. So that's how we replace dx with d theta. What about r? Okay. You see, again, a is a constant, which I want to keep. I don't want to have x in there anymore. So how do we relate r and theta? You know, a over r equals cosine theta, right? A over r equals cosine theta, right? So what is r equal to? R equals a over cosine theta, right? So let's do that. So r equals a over cosine theta. So I'm going to plug this and this both into the expression for f. And let's see what this integral becomes. Okay, dx is replaced by a secant theta squared d theta, and 1 over r, and r squared is replaced by what? A over cosine theta squared. Right. Now let's clean things up. There's a squared, so overall it's k sigma over 2 pi. A is gone. See, a is gone. Okay, there's no a here anymore. And let's see, is there any further surprise here? What you have here is secant squared theta and cosine squared theta. Am I right? And d theta, right? Is there a yes or no? I'm just, you know, I just flip cosine theta up, right? And where does theta, what's the upper and lower limit for theta? You have to go all the way to this way to that way to cover the entirety of the infinite large sheet. So theta goes from negative half of pi to positive half of pi, right? So theta has to go from negative pi over 2 to positive pi over 2. What is this equal to, folks? Secant is 1 over what?
Cosine.
Yes, so secant theta squared times cosine theta squared equals 1. Isn't that great? Okay. So after all this, we found a rather simple answer. The integral becomes what? Pi. Okay, so the final answer is k q sigma over 2. Okay, and k and this answer, it took us quite a little bit of effort to work out. Well, fortunately, this integral that we end up with is rather simple at the end of the day, you know, because secant theta and cosine theta, they're reciprocals of one another. But still, it took us a while to figure it out, right? And you will see when we revisit the same problem in the next chapter, how we can solve this problem in a matter of 10 seconds or 20 seconds.
Professor, I have a
Yes.
question about the
Yes.
lambda, how you take the sigma into dx.
Okay, lambda by definition, here's how we define lambda. You have a strip of charge, and it's got a width of dx, right? Width of dx. By definition, what's lambda? Lambda is you take a unit length of this strip, unit length, 1 unit in length. I count how much charge there is. That charge is called lambda, charge per unit length, right? Agreed? That's what lambda means, charge per unit length. Now, how much charge is contained within this strip? We don't know lambda, we only know sigma. Sigma is charge per unit area. So what is the area of this strip? The area of the strip is dx times 1 unit, right? That's the area. Length is 1 unit, width is dx. Okay, you take that area times sigma. Don't you get the amount of charge contained in this strip? Okay, and that is by definition, that's lambda. Because lambda is the charge per unit length, right here. Right?
Yes, thanks.
Okay, very good. So that's how we do it. Yeah. Okay. Any questions, folks?
I think I understood pretty much everything, but when you integrated from pi over 2 to negative pi over 2. Why is it that you did that?
Because this, in the middle, theta equals 0 in the middle. Okay, if you one direction is positive, the other direction is negative. All right. What you can also do is integrate from pi theta equal to 0 to theta equal to pi over 2. Pi over 2 means you're looking this way. That's how you look at infinity. And you multiply by 2 because there's equal contribution from both sides.
I see. All right,
Yeah.
thank you.
You're welcome. Any more questions, folks? Okay. If you don't have any questions, we can get on to next order of business, which is our lab. Okay, so let me do a new share with you for the lab. I'm going to share the desktop with you this time. Desktop. Okay. For the lab, you click the lab report instruction. That's how you get to the lab. And you click Coulomb's law, which is our virtual lab today. This will give you instructions as what we do. Okay. This is the virtual lab. And it's made of 2 parts. The first part is a simulation. The second part is a video lab. Okay. Now, I made an earlier announcement telling folks that in order to access the video labs, we use a paid service called Pivot Interactive. And because it's a paid service, you guys have to register first. We already paid it for you, okay? So, but you have to register. You have to click this link here. It's going to take you to a registration.
Professor?
Yes.
You're not sharing the screen.
Oh, I'm sorry. So let me do a new share desktop. Can you see it? Can you see it
Yes,
now?
but too
Okay.
tiny.
They're tiny. Hold on. Are they bigger now?
Yes, yes. Yeah, it's good.
Okay. Okay. Coulomb's law. See, there are two parts in Coulomb's law. Okay. One is a simulation. The other is a video lab. Now, for the video lab, you're going to have to register here. You click this button here. It's going to take you through the registration process. You know, if you haven't done so, please do that. Okay, because it's a paid service, so that's why they want you to register first. You're not paying anything; they will pay it for you. So there are two parts. Both of these deal with Coulomb's law, and the first part is really simple. It's a simulation. You want to verify this formula here, and the way you do that is take a natural log of both sides. Natural log of both sides. Okay, and that's going to get you you know, auto to the power. It's auto to the power -2, right? So when you do natural log, don't you get auto to the power -2 here and natural log of r and then plus a constant, right? Now, if we don't know whether it's -2 or not, we just say -n, then you're going to get a -n here. And how do you know n equals 2? How do you know n equals 2? Well, what you can do is if you can collect data of F1, R1, F2, R2, F3, R3, and so on, then you do a plot of natural log of f versus natural log of r, you can get a straight line. Any power function after you take a natural log becomes a straight line, and the slope is that power. Okay, if y equals x to the power 3, for example, you take natural log y versus natural log x, you're going to get a straight line, and the power 3 becomes the slope. Okay, the slope equals 3. Now in our case, the slope equals -n. N should be equal to 2. Ideally, is that true? Well, you're gonna do this measurement yourself. Okay, so I am going to take you to this. That's when you do the first part of the lab simulation. It's incredibly simple. You can either do macro scale or atomic scale, either way. Okay, so here's charge. Here's charge. You can move these charges to different location. Okay, so R is the distance between center of Q1 and center of Q2. So for example, in this case, it's between 3 centimeters to 7 centimeters. So R equals 4 centimeters, okay? And you can change that. So the force now becomes, the distance becomes 3 centimeters. And here distance becomes 2 centimeters, and so on. And you can see the force changes, right? The force changes, okay? So you collect a bunch of values of F versus R, and you take natural log of both sides. And you do a plot of log F versus log R. Do you get a straight line? And if you do, what is the slope of that straight line? Should be -2. Ideally, it should be -2. You can see that for yourself. Okay, and so it's incredibly simple to do, actually. Right. So that is that part, the simulation. And here it tells you what to do. Right, the details what to do. Now the second part is a little bit more interesting. It's a video recorded lab on Pivot. Again, you have to register first. But let's see how Pivot works. Okay, I have opened up a window for Pivot for you for this lab. Okay, and so here's what they do. They have a pair of metal spheres. As a good approximation, you can think of the sphere as a point charge at its center, which is marked by this white line here. So the white line here is a white line here. That's where the center is located. Okay, and let me blow this picture up a little bit. You can see it better. Right now, there's a reading here. The reading is the force acting on the scale. There's a reading. So you start. Okay. Let me start by playing this video. Right now the reading is 0, Now, give you some charge. This disk has some charge on it, and when you put that disk in contact with red sphere, it transfers some of the charge to the red sphere. Okay, so the red sphere becomes charged. Okay, becomes charged. But you see, hold on. They re-zeroed it. There we go. The number is almost zero. Okay, at this point, the lower sphere is not charged. Only the upper sphere has been charged. Is there any electric force between them? Tell me at this moment. When only one charge, when only one sphere is charged, the other one is not. Is there any electric force? Obviously, no, right? It takes Q1 and Q2, or Q2 equals 0, right? And this is where they zeroed it. So the number is almost 0. I mean, it's 0.00001 Newton. It's almost 0. Okay, so that is to say they don't count any weight or anything like that. This is what they just only count the electrostatic force, which is 0 at this point. Now, watch what happens next. This guy is going to bring some charge to the lower sphere as well. There we go. So now both spheres are charged. See, there's a reading. This reading is what? The electrostatic force, the Coulomb force between the two spheres. Okay. There we go. See, right now the force is what? 1.00108 newtons, right? With that distance, okay? As they bring the two spheres to closer, what should happen to that reading? That reading, should it increase or decrease? Should increase, of course, right? So let's bring them closer. See that number increases? 25 newtons, 26, 27, 28, 29, 30, and so on. 32, 34, 36, see that? That number increases as the spheres are brought closer. Your job is to pause this video at various moments. Measure the distance R and measure the force. Measure another distance, measure another force. Then you can plot F versus R. Or actually, more precisely, natural log of F versus natural log of R. Okay, but how do you find the distance? Well, here's what you do. Here's what you do. You see this corner here? Press this corner here, and you can deploy a scale. There we go. See, right now the scale is, you can always start from here. You know, the 0 centimeter to be aligned with the center with a white line on the lower sphere. Right now, the top one reads what, 28, right? 28 centimeters. Okay, so that's a data point. Okay, the reading is 0.00036 newtons. Now, bring them closer. Bring them further closer. Okay, let's say we stop right here. The number is now 0.00049 newtons. The distance between them is 22 centimeters. See that, 22 centimeters. And just keep on doing it for more readings. Okay, for example, here is 0.0081 newtons, and the distance between them is what, like about 11 centimeters, and so on. Right? Just collect some readings, and then you have a bunch of F with a whole bunch of R's. And again, take natural log of F versus natural log of R. When you plot, do you get a straight line with a slope of -2? That's what I want to know. Okay. So essentially the same goal as the first part, except this one is not a simulated lab. It's a real lab somebody did. We just analyzed the video of the recording of the lab. Okay. Questions, folks? So there's detailed instruction here. All right. One more time, any questions?
So it's a group report, right?
Yes, all 1C reports are grouped by default. If you really want to do individual lab report, you can opt to do that. I would encourage you to do group reports because you want to see how you work together. Most of the projects you work in a real life, in a company, most of these are group projects. So yeah, if you click on lab report instructions, here it tells you all labs are done in groups and all Wednesday lab reports are group assignments by default, even though you can turn in individual ones if you wish. Okay, folks.
Yes, I see, Professor. Thank you.
Very good, very good. So if everything goes as planned, by this time next week, we'll be in the same lab room doing an in-person lab. If there is any change, you will be notified. Okay. So that's pretty much all the discussion I have planned for today. Do you have any questions? Everything's still cool, right?
Yeah, I just need to review some calculations and formula and do the homework.
Yes. So we're all good. Oh, hold on. Hold on. Yeah. Okay. Pretty much. Yeah. Okay. Somebody has. Hagop, you have a question?
Yes, sir. I see that. So for Sunday's quiz and for anything moving forward that we're gonna get quizzed and tested on, you said that the best way would probably just stick to the homework, the best preparation for us.
Yes, the homework problems and the sample problem, those are closest to the real problem you will receive on a test. Yes, even though I must say that when it comes to homework problems, some problems will be a little bit easier than the test problems, some problems will be a little bit harder than test problems. Okay, so the average quality of the homework problem will be in line with the test problems. Yeah.
Okay. Perfect.
Quizzes, on the other hand, are generally much simpler than multiple choice questions.
All right. Thank you.
You're
Appreciate
welcome.
it.
Yeah, and if you click on syllabus here, right here, this is not real syllabus. This just gives you a list of what's due, like what's due here and here. So yeah, this will give you, if you click into that, you can see what comes next. Okay, so you won't miss anything.
Thank you.
All right, very good. Any more questions, folks? Okay, so I'm gonna stop the recording for now.